So today we are going to discuss about Fick's laws of diffusion, and those laws are based on mainly on the concentration gradient. Okay, so Adolf Fick actually proposed that the flux is one-dimensional system is proportional to the concentration gradient. Now we have to understand how this flux is represented and how concentration gradient are going to take place with respect to movement of mass, or if you tell that flux movement from one portion to another portion through a particular region. So if you take an example, suppose for annealing, so if an inhomogeneous single phase alloy, if it is annealed, and the method or the mass will flow in a manner which will decrease the concentration gradients. Okay, now what is annealing? As per the materials engineering perspective, annealing is like that when you are heating a one metal sample to certain high temperature, and then you perform the furnace cooling. I mean, you are keeping the sample in the furnace itself, then switch off the furnace, and slowly furnace is cooled down, and that material also cool down. So that will be a slow cooling process, and that leads to a scenario where the object or specimen will be either get rid of residual stress, or the residual stress is reduced in the specimen. So this is the actually main objective of performing annealing. So if you are annealing such kind of inhomogeneous single phase alloy, what will happen at high temperature? The matter will flow in such a manner that it will end up the time which will decrease the concentration gradients. If the specimen is annealed long enough, you are giving the time of annealing is very long, then it will become homogeneous, and the net flow of the matter will slowly cease. It will be stopped. So if you look at such a way, and then if you want to understand what Fick's has proposed in his first law, if you see in the slide that J, which is a mass flux, and J is varies to minus dc dx and equal to minus d dc dx. D is the diffusion coefficient. So in this equation, you can see that the unit of J, capital J, is mole per meter square second, and is a flux, and D is the proportionality constant, that is the diffusion coefficient, you can tell, and C is the mole per meter cube, is the concentration, and X is the Poisson vector. So here what we are talking about, we are talking about one dimensional, means in the X direction the mass is flowing. So in the conventionally we are taking very simple representation of the first law, that one dimensional is flux. Then if you talk about this kind of concentration gradient based mass transfer, then you have to very much careful, because you have to name it as a downhill diffusion, because we know till that discussion that there is another kind of diffusion, that is uphill diffusion. This is not governed by concentration gradient. Okay, so the negative sign, first we will start to understand the why this negative sign is there. The negative sign emphasizes that diffusion occurs down the concentration gradient. So you can name it as a downhill kind of diffusion. Okay, but it is not necessarily true for every system. Already I told that there is another thing, that miscibility gap or uphill diffusion concept, that is not true. So what proposed by Fick in his first law of diffusion is not always true. Okay, for some system it is true where downhill diffusion is occurring. So diffusion of a component generally is governed by chemical potential gradient, that we understood very well till now. The components always diffuse down the chemical potential gradient, and if this leads to a diffusion of component up to a concentration gradient, then we can tell that it is the uphill diffusion, not downhill diffusion. So in the slide, if you see, you can check that in a conventional downhill diffusion, the diffusion coefficient gives a positive value. But whereas the diffusion coefficient gives negative value in the case of uphill diffusion. So now we understand that this kind of Fick's first law is actually based on concentration gradient where downhill diffusions are occurring or it is prevalent. So this is to derive the relationship or relation for the estimation of the diffusion coefficient, and then you can understand how normal downhill diffusion, that estimated diffusion coefficient will be positive value, and however it gives a negative value if you are talking about a uphill diffusion. So this is most important understanding with regard to Fick's first law. So you must remember, although Fick's first law is used to derive the relations for the estimation of the diffusion coefficient, now we can say that it is not alone sufficient to explain the time dependent or non-steady diffusion profile. It is difficult, and also it is not alone to all kind of diffusion process, because it cannot explain the proposition of uphill diffusion. Okay. So this kind of first law only can be used directly if there is no change in concentration profile with time. So in the first law, you are not having any time component. So you cannot explain the time dependent or non-steady state diffusion profile. So it is also a limitation of the Fick's first law. And another, if you want to look it into more critically, then you can tell that it can be applied directly only if there is no change in concentration profile with respect to variation in time. That is almost impossible to find in most practical example in metallurgical industry sector, metallurgical phenomena sector. So this is a real problem to apply Fick's first law in all kind of metallurgical phenomena, because mainly things are very unsteady or it is dependent on the time, the diffusion profile or concentration profile. That cannot be explained by Fick's first law of diffusion. Now we try to understand what is Flux equation, what is diffusion equation, and it is really is correlating with the Fick's first law of diffusion. It can be said that to take the flux across a given plane to be proportional to the concentration gradients across that plane. Means if you put a plane perpendicular to the mass transfer, so if you see that, for example, if you take x-axis parallel to the concentration gradient of the component 1 and the flux of the component 1, you can take capital G1, then you can describe, if you see in the slide, that G1 equal to minus D1 in the bracket del C1 del X at particular time. So where D1 is represented as a diffusion coefficient, and this equation can be also named or another form of Fick's first law. And this actually fits the empirical fact that flux goes to zero as specimen become homogeneous. So in the process, when there will be no concentration gradient, then the specimen become homogeneous, and then only the flux goes to zero. How can you understand from the mathematical expression? Because when there is no concentration gradient, it is become homogeneous, then del C by del X will be zero, then flux also will be zero. So that is the physics-based interpretation of that mathematical expression, that the specimen become homogeneous when there is no flux movement. The flux goes to 0. And although it did not to have the case that if you see that experimentally show that D1 or equivalent the ratio of minus G1, the concentration gradient is independent of the magnitude of the gradient. That is also very important thing. So if you see in the slide that here G1 we understood that is a flux of component 1, and also we understood D1, del C1 and del X. Now D1 is the coefficient of the diffusion coefficient, and if you write in the diffusion coefficient, and then you can write del minus D del C by del Y. That way you can also represent for different things. Now we are going to understand about what is difference between Flux equation and diffusion equation, or we want to understand what is diffusion equation. And before that, you should know one thing: the dimension of that Flux equation. J is mass per length square into time. It is the one dimension of the J, that is flux, and D's dimension is the diffusion coefficient has dimension L square by time. And if you look at del C by del X, it's a the dimension will be mass per length Q, means mass per volume is the concentration, and also the del X is the length L. So in this way, you can also check how the equal dimension from left hand side and right hand side of the equation sign. So that diffusion coefficient has usually been given in the units of square centimeter per second. Now we have to little bit I want to introduce one word, that is symmetry. Symmetry, what is that? Symmetry means all the direction or the direction you are interested, are there symmetrical or asymmetrical? How you can understand? If there is a after certain point the repetition is there, any periodicity is there, that is one kind of symmetry. If you put a mirror, if you imaginary mirror in a particular plane and try to find out there is any same thing, same image is there, and that image are repeating with certain distance, then you are going to symmetrical. And cubic symmetry is it looks like at each unit of atomic arrangement in a three-dimensional, that is in the cubic. So in a lattice with a cubic symmetry, the diffusion coefficient has the same value in the all direction. So it is symmetrical. So you can tell that the alloy is isotropic with respect to diffusion coefficient. So the assumption of isotropy will be made, will be very important, and we will discuss throughout the subject where we are looking at to the diffusion. We used to look at isotropy concept with respect to the specimen. We will consider during this subject if we are looking at diffusion coefficient. Now we are going to concentrate on diffusion equation. Suppose if a steady state scenario is not exist. What is that? If the concentration at some point is changing with respect to change in time, means with respect to time, concentration profile is changing, is varying with respect to time, the concentration. Then if such scenario happen, then what will going to happen? It is not a convenient form to use what we understood till now. So in order to get more useful equation, it is necessary to start with second differentiation, and that is required. And how you are going to obtain that? If you go for simply material balance. What is that? Suppose an element in the picture also you can see in the element del X thick in throughout the X direction. We are looking at the X direction, and the bottommost picture you can concentrate or you can observe. There is a thickness of del X at X direction along the X axis, has flux J1 in one side and J1 in one side and J2 out other side of that del X thick portion. Now, if del X is very small, what will happen with the J1? J1 can be accurately related to J2 by the expression you can see in the slide. If the del X is very small, J1 directly can be correlated with J2 using the expression given in the just bottom or below the diffusion equation title. Now, since the amount of material that come into the element in unit time J1 is different from which left J2, there will be a concentration, the concentration gradient. The concentration in the element, if you look at the del X as an element, which has changed the volume of the element, now we can talk as a del X multiplied by 1 because unit area times of the thickness. Other y and z direction, there is a unit value, so unit area thickness you can talk. So the net increase in matter of the element can be calculated. My J1 minus J2 will directly, you can get that del X into del C by del T. In this way, you can get the difference of the flux, that is J1 and J2 across the element having thickness at x axis del X and other two axes throughout the unit dimension. So in this way, you can understand that here we are looking at also the time concept when you are looking at the diffusion equation. That one is flux equation, one is diffusion equation. Now we are going to understand second law of Fick's second law. So here we are having a understanding that there is a flux equation, there is a diffusion equation. And in case of diffusion equation, we are actually looking at the time component also. We are looking at time component, that is del C by del T. Already we have discussion. Then again we start from that position. J2 minus J1 or J1 minus J2, if you are del X del C by del T, it's equal to minus del X del J by del X. So in this way, what we are going to get, if you check that first equation is valid at any instant, even in the concentration and concentration gradient at the point, at particular point are changing with time. Even there is a change in time, change in concentration gradient and concentration at particular point with respect to time is happening, still the equation is valid. That expression is valid. Therefore, we can easily substitute and can write that del C del T equal to del X of capital D into del C del X. And that is actually Fick's second law of diffusion. Okay. Now for getting more generality, what we can do, one can do for three-dimensional, and we can use the vector notation, that can be written like del C del T equal to minus del of J. Del, always we know that del X plus del Y plus del H represented by the del of that. So this is called, also you can check that this is also is a content equation and stems only from the conservation of matter. So it is actually coming from the stems from the conservation of matter. So if you look at the slide, also you can understand what is flux, how flux is defining, and then slowly you can understand that if the diffusion coefficient is isotropic and it's not dependent on the space variable, then you can take out the diffusion coefficient from the del X part. Then what will happen? We are going to get a del C by del T equal to capital D into del square C. So in this way, you are going to get such a representation of Fick's second law. Now we are going to understand the diffusion equation solution when the diffusion coefficient is constant. That is steady state solution. We are going to look at first steady state solution, then unsteady state solution, both. So it is very simple that if you are looking at steady state solution for that, so what you have to look at, that first condition for that, concentration gradient with respect to time or variation in concentration of a particular position with respect to time will be 0. So you can directly write del C by del T equals to 0. So if you write that, if you write that, you have to very cautious about the one statement that you are able to write that because the D is constant, so you can keep out of D. So del square C, you can tell that Laplacian of concentration and its representation in different coordinate system can be done. So now things are very simple. If you are looking at a steady state exists, then del C by del T must be 0. And in this process, the whole scenario reduced to a mathematical expression, that is capital D multiply of del square C equals to 0. And you can take out from del square C this D and from D out of that expression, because you are considering that D is constant with respect to space and time. So that's why this steady state solution of diffusion equation you are going to get when there is a no change in diffusion coefficient, means you are looking at constant D. So the simplest case, if you look at the Cartesian coordinate, what you will get? D into del square C by del x square equals to 0. Now you can solve it and you will get different position, the concentration. So concentration as a function of space variable, that may be, if it is one dimensional then only x, if it is two dimensional xy, if it is a three dimensional xy and z. Now we are going to understand what will happen with the non-steady state solution. If D is not a function of position only or composition, it is also determine the concentration as a function of position as well as time. Means now you have to find out C of x comma t. So for that, what is required? Now you have only told that this is unsteady state, then you are doing that. Now you have to go for initial as well as boundary condition, both are required, because you have to solve scenario such a way that with respect to space and with respect to time, how concentration is varying. So now scenario is different. So that del C and del T is no longer is equal to 0. So when the diffusion distance is sought related to the dimension of the initial inhomogeneity, CXT can be mostly expressed in terms of error function. That is a mathematical approach. We can revisit that part. That is a error function based calculation that is there. But this is just a method of get the solution of second order partial differential equation. What is actually mathematical expression for the Fick's second law. So now we understood Fick's first law and second law and how both laws are different, in what way they are important for which cases and how to solve that, and to solve those things, how diffusion coefficient you have to certain times take as a constant, or if it is a function, then all those things you have to understand. Now we are going to take a case of metallurgical engineering sector and metallurgical industry and try to understand how we are going to solve the Fick's second law in case of homogenization. Please, I am giving 10-15 seconds, please look at the picture, that concentration gradient. There is written that T equal to 0. This is a black color, and slowly the dotted line shows that at when T is tau, means T is more than is more than the initial time period. If initial T equal to 0, the tau can be 5 seconds, 5 minutes, or 5 hours. So it is slowly the progress in the process. Please look at that picture of concentration gradient. I am giving 15-20 seconds, then I'll again try to explain so that you can understand. So you have observed the picture. Now we try to explain it. So here we are discussing about one case when homogenization means you can take the annealing process very much longer time. So the concentration gradient will be reduced to 0 so that whole specimen will be homogenized. So from non-uniform to uniform, you want to get the concentration profile inside a specimen. Suppose you are going to consider a composition profile as superimposed sinusoidal variation. If you see in the picture, this picture is a sinusoidal variation, and it actually representing the concentration profile, where the solid line, already I told you, represents the initial concentration profile, that is at T equals to 0. And if you look at the dashed line, it represents the profile after certain time. You can tell that is a tau time. Tau can be 1 minute, 2 minutes, 90 seconds, or 1000 minutes, or 5 hours. Does not matter. So based on that, you can get when the time is varying, what will be the concentration profile. So at T equal to T0, if you look at the C equal to C bar plus beta 0 sine pi x by L. That is very simple representation of any sinusoidal curve. It's a very basic mathematics we learned from +2. Now, if you apply the Fick's second law, where D is diffusion coefficient and del C by del T is concentration gradient with respect to concentration variation with respect to time in particular position, and del square C del x square, we can tell that it is also the double derivative of concentration with respect to space. And here is I am taking example of one-dimensional case. So x-axis we are taking. So at time t, what will be the expression? C of xt will be C of C bar plus beta 0 sine pi x L into e to the power minus t by tau, where tau is L square pi square d and tau is defined as a relaxation time. It is very good concept. Here you are telling that at time t, suppose you are telling that kind of solution, then you have to give certain relaxation time in order to get the homogenization portion, homogenization kinetically completed. So you can tell that the largest deviation of concentration at x equal to L by 2. It is a very simple mathematics if you use. And then what will happen? the sin pi x L equal to 1, and that is the maximum. So it is an exponential decay. You can tell the longer the wavelength, that is L, and the longer the relaxation time, that is tau, then the slower will be the decay. So if you increase the wavelength and longer the relaxation time, slowly, you are allowing the relaxation process, then the decay of the concentration gradient will be also slow. To short wavelength dies fast, means it decay will be very fast. That's why shaking always helps speed up the dispersion. Now we can understand from this homogenization process, when you are doing shaking, what you are doing? You are reducing the wavelength, that shorter wavelength, and that actually the help to speed up the dispersion process, because it enables wide spreading means lower the or smaller the L of the stuff that like particles you try to disperse. So now very critically, please take this example again. I am telling, take time to observe the concentration profile here. From the sinusoidal concentration profile, what we understood, the largest deviation of concentration will be at x equal to L by 2, when sin pi x by L equals to 1, that is maximum. So it actually indicates that it is an exponential decay. So if you have the longer wavelength, longer will be the relaxation time, and that leads to the decay process will be slower, and shorter wavelength will be advantageous to get faster decay. So therefore you can tell that if you shake a solution, shake a mixer, then shaking is always going to beneficial for speeding up the dispersion process. And why is it so? Because it enables wide spreading. It allows the wide spreading, and wide spreading actually wide spreading means that helping to get the smaller L of the stuff like particles which you are going to disperse or which you are trying to disperse. So now you understand that application of second law is very viable, even a very simple cases or practical cases of homogenization of a metallic specimen, if you are talking about metallurgical aspect or metallurgical engineering aspect. So this is a good example of understanding how to solve a Fick second law if you are taking care of a case of homogenization. So today lecture is over. Thank you.